So today we're going to move on with rational functions a little bit, talking about multiplying and dividing them. And it's kind of the same skills we've been using, but to factor and reduce and all that stuff. But you just got to think about it as why multiplication works with fractions the way it does, and then it kind of clicks into place. That's why we have this warm-up where you just have two regular fractions. It's the same skill, we just need to push it forward. But before we do that, let's take the time on the homework if needed. So grab your homework. Now, for this lesson, for this warm-up, you might have done it differently than I'm about to do it, okay? In fact, we'll do it your way, and then I'll show you my longer way that's like, well, why do all that? For today's lesson, that's why. Okay? So if we're multiplying fractions, what's the rule? What do we say we do? Just multiply across, right? That one to that one, that one to that one. So then I do that, and I get what? 60 over 150? Is that right? Okay. Now, when I finish multiplying, am I done, or do I have to check? I have to check if I can simplify. What goes into both of these? 2, 10, 30, 15. All of those are true, right? So you might end up simplifying and then having to simplify again because you see something else in there. And unless you're lucky enough to get to that biggest one first, right? You might say, okay, let me try 2, divide by 2, and I get 30 over 75. And then what do I see? What goes into both of those? 5, okay, so then I divide by 5, and I get, what do I get? 6 over 15. Are we not done?
No.
Yeah, because what goes into both of those? 3 and 3, and I get 2 what? 2/5. Okay. So, totally fine. That's the way we've done it. It looks like we could have divided by 30 right away, gotten there, right? But this happens a lot, where you think you've reduced it, and then you haven't, and you're like, okay, I got to keep going, and it takes more time than you thought it would. Now, if you got to 30 right away, that would have been quicker than I'm about to show you. If you find yourself doing this a lot, I can give you the way that will get you right to where you want to go right every time, okay? Now, when we multiply across 12, 5, what do we end up doing? We end up making one big fraction with the result of what at the top? What ends up at the top? Just tell me the operation. What was the operation to get there? 12 times 5 was on the top. And then what was on the bottom? 25 times 6 on the bottom. Now, that's exactly what we did, but pay attention, please. That's exactly what we did, but this is an important distinction. What are we doing when we multiply two fractions? We're just making a third fraction with everything on the top, everything on the bottom, right? And that's going to help when we get down here, okay? Thinking about it that way. You're just making one big fraction with the stuff from the individual fractions together multiplying, right? Now, if we've decided to factor these instead of multiplying them, so instead of going up to 60, we break them down. What is 12 in terms of factors? Well, 1 doesn't help us too much in this case, but you're right. 3 and 4. Can we keep going any further there? Bring it all together. 3. What does 4 break down into? 2 and 2. So 3 times 2 times 2 times 5 now. On the bottom, 25 can be what? 5 times 5, and 6 is 2 times 3. Okay? Just break them down as much as you can, right? And then what do we see on the top and the bottom? The same thing on the top, same thing on the bottom. What do we do when we see that? Cancel. So what can cancel? 5 and 5, 2 and 2, 3 and 3. What am I left with? 2 on the top and 5 on the bottom, which is what we got to eventually up there, right? So these are just different methods to do the same thing. You could see how like this could be quicker if you got to 30 right away than having to break these down on the way. But that actually ended up being quicker than what we did because it took us so long to get there. And this will always be the same amount of steps. This will vary. So if you just want to lock in on this, you'll be in great shape for reducing fractions. And you, what's that?
What's that one method called where you cross-multiply?
Cross-multiplying is about solving.
Oh.
We are not solving right now. We're just multiplying. Okay, now this method is super important for what we're about to do here. Okay, so let's take a look here. Now, what did I say? When you multiply fractions, it's like making what? One big fraction, right? With this times this on the top, so 5x to the third times 9x squared on the top, and this times this on the bottom, 9x times 4. Okay? Now, you might say, why not just do the multiplication, put the result over there? Same reason I did just a moment ago. Factoring actually helps us here. Keeping it apart actually helps us here. It's going to help us see what cancels. And in fact, I could factor this even more. This is actually 5x to the third, if I factored it out, would be 5 times x times x times x. And then what is 9 factored down? 3 times 3 times x times x. On the bottom, I have 9x. That's 3 times 3 times x. And then 4 is 2 times 2. Now, this is kind of like anything else. If you can kind of see reducing really easily, you might not need this method. But if you can't, if you're not great at reducing, this gives you a fail-safe method, right? Because now when you break it down all the way, all you do is cancel. So what do I see on the top and the bottom? Something that showed, yeah, 3, 3, 3, 3. What else shows up on the top and the bottom? One of the x's, right? Okay. And now when I bring it all together, I just say, okay, what number do I have left on the top? 5. How many x's? X to the 4th. On the bottom, I have what? 2 times 2, which is 4. Okay? Now, you could have gotten that by doing 45 and 36 and reducing it. But that seems like a lot more work to me than not leaving it separate and then cutting out what you can, right? You could have gotten that by getting x to the 5th over x, using the quotient rule, subtracting, ending up with x to the 4th, right? But this will work all the time, okay? Whether you see the tricks or not, this will work all the time. All right? How about this one, multiplying? So what do we end up with on the top? 5 times 7 times x. And on the bottom? Yep, 2 times 3 times x times 5. Okay? So I look for stuff on the top and the bottom. What do I see? 5 and 5, x and x. Okay? And on the bottom I end up with, on the top I just have 7. And on the bottom I have 2 times 3 times 3, so that's 18, and then x, just x, right? Yeah. Question? Okay. Now, this process, maybe for these you don't need it. Maybe you're just like, I can see that 5 and 15, that would reduce, give me a 3 on the bottom, 6 times 3 is 18, x over x squared, that cancels, leaves me just x on the bottom. Maybe you can do a lot in your head. Maybe you can't, and you need this. Maybe you can, and you don't. But for the next part, you need this process, the breaking it apart part, the canceling part, no matter who you are, okay? And that's because, what if you end up with something like this, okay? Again, we're just going to write the factored out parts, right? So first I make one big fraction with the top and times the other top. So what's the first top that I have here? X times what? X minus 3, the whole thing as a group. Okay? On the bottom, I have what? X squared minus x minus 6 times 1. I mean, times 1 is just itself, right? But we'll reduce that in the next step. Now, I'm going to break apart, just like I did up above, the bottom. How do we break apart a trinomial? Run. How do you break apart a trinomial? Magic X. So if I magic X this, what do I do? It would be x minus 3 and x plus 2. If you have to magic X that on the side, go for it. Okay? But that's what it would break into. Now, I see what cancels. Just like above, I factor it down a lot, top and bottom, and then I see what fully factored top, fully factored bottom, I see what cancels. What cancels here? X minus 3 and x minus 3, which leaves you with just what on the top? X. On the bottom, x plus 2. Okay? So that, just to remind you what we're doing this whole thing times this whole thing, and that's our result. It ends up being x over x plus 2.
The 1 just goes away.
Yeah, because anything times 1 is just itself. Okay? So, now, does multiplying make sense? You multiply across, you got your one big fraction, you factor it out, and cancel. Okay? Now, dividing, that will be involved, but there's a keep, switch, flip first. You got to remember how to divide fractions. Question? Because if I did x squared minus 3x, the next thing I would have to do is factor out x again. So I can cancel out the x minus 3. Like, if you multiply it out, sure, but then wouldn't I need this factored so I could cancel the x minus 3? So I would end up just factoring back out the x, which would be an extra step I don't need. That's why I say leave it factored, factor it out fully, see what cancels, because you might have to factor anyway. Okay? All right. Now, you will need to remember something for this. Keep, switch, flip. Okay. To divide fractions, keep, switch, flip. Remember those words because I'm zooming in. What do I keep? Does anybody remember? The first thing, right? This is 1, 2, 3 in terms of keep, switch, flip, right? Keep, switch, flip. Okay, so I keep 2/3. I switch. What? Not the sign. Well, kind of the sign, the division sign. Like not the positive or negative sign. I switch division to multiplication. And then I flip 15 over 7. Or 7 over 15 to 15 over 7. All right. And then it becomes just like the front. Now I'm just multiplying fractions again. So I end up with 2 times 3 times 5 over 3 times 7. What cancels? The 3's, and I end up with 10/7. Okay? All right. Now, all we got to do, see, so these become the front, right? You get the key, switch, flip to start, and then it just becomes like the front. It's just, now it's multiplication. But the first step is if you see division, you have to switch, flip. Okay? All right, so take a look at this one. Okay? So what am I going to keep? 7x squared over 9. What am I going to switch? Division to multiplication. And what am I going to flip? So I make it 21x to the third over 3x. Okay? Now I make it one big, now it becomes just like the front, right? I make one big fraction, and I break it down. I got 7 times x times 7 times 3 times x times x times x. On the bottom, I have 3 times 3 times 3 times x. And I see what cancels. So what would end up canceling here? One of the 3's, and what else? 1x, and then there's nothing else that I see on the top and the bottom. So I bring together what's left. 7 times 7 is 49. X times x times x times x is x to the fourth. 3 3 times 3 is 9. And I end up with my answer, 49x to the 4th over 9. Okay? All right, what I'll do is, well, we got about 13 minutes left. Do we want to continue to see examples or just start practicing? Do we want me to just skip to the hardest example? What do we want? Do we want me to just go through them all? Look at 3? Okay, let's go to 3. All right, so number 3. All right, so the first step, there's a lot going on here. The first step is keep, switch, flip, though. So the first thing I do is keep, switch, and flip. Right? Keep, switch, and flip. All right, so I got to change the problem before I even attack the problem. All right, so keep, I would have x plus 6 over x squared minus 4x minus 60. Switch to multiplication, and then flip this to x squared minus 5x minus 50 over x squared minus 4x minus 21. Okay, now, we said we're going to make it one big fraction, and then we're going to factor it out, right? So this will be a big fraction. What's on this side on the top? X plus 6, and then on this side, x squared minus 5x minus 50. On the bottom, I have x squared minus 4x minus 60, and then x squared minus 4x minus 21. Now, there's a few things I need to factor here, right? I need to factor that. I need to factor that. I need to factor that. How do I factor each of those? Magic x. So you're going to have 3 magic x's here in one problem. Okay? There, there, and there. Right? You got to do all 3 and then see where you land. Okay? So what does that look like? You end up with x plus 6, and then x squared minus 5x minus 50 would be x minus 10, x plus 5. Okay? That gets you that. Okay, on the bottom, your first group, x squared minus 4x minus 60. Anybody? X plus 6, x minus 10, right? Minus 60, minus 4. And then on the other one, I have x minus 7, x plus 3. Okay, so everything's fully factored out. 3 magic x's later, we can start looking to see what cancels, all right? X plus 6, do I see that on the top and the bottom? Yes. X minus 10? Yes. X plus 5? No. Any of the other stuff? No. So I end up with x plus 5 over x minus 7, x plus 3. Okay? And I think that's your fully hardest version of this. 3 magic x's in one problem. Okay? All right, so I want you to try 1, 2, and 4. Work on those. When you finish those, I'll give you your homework. All right, so number 3. Okay, so remember, there are different pieces that we need to find, of course. And there's different steps for the different pieces. Bless you. Okay, so let's talk about the pieces, right? What's one piece that we always try to find? What is it? The VA. Vertical asymptote. What else? Horizontal asymptote. What else? Holes. Anything else? X-intercept, if any. And the y-intercept. Okay, if any. Now, there's some of them you can find whenever you want. Some of them you need to do a little work first, right? So where would we like to begin? Because you kind of can begin at different spots here. Kind of. Yeah. Horizontal asymptote. Why could we start with the horizontal asymptote right now? Like, why don't we have to do any work to that first? Because you just look at the original thing that you have, and you look at the beginning of it, and you think about, what do I have in terms of my degrees, right? So the horizontal, we could actually do right now. And you just look at this and this. And you say, higher degree, lower degree, what's the degree situation? The bottom one has a bigger degree, which makes this bottom heavy, which means we always have a horizontal asymptote of 0. Right? So we know that we have a horizontal asymptote of y equals 0 because we're bottom heavy, which means straight across. Okay? In the back of my mind, I think to myself, boy, if I have a horizontal asymptote, am I going to have an x-intercept?
So it just goes against the x?
Yeah, that's where y is 0, right? Right? Are we gonna? Do you think we're gonna? Let's make a prediction. You think we'll have x-intercepts here when we get there? Probably not. If I can't put a point there because there's an asymptote, we'll say that. Okay. What we'd like to do next? I think no matter what, we're going to have to what? Factor. So we'll start to factor this. All right. What can come out of negative x plus 3? A negative 1. So then it just becomes x minus 3 on the top. Right? If you have a negative in front of your x or a negative in front of your x squared, it's not going to work for you. You've got to pull that out of everything. So you pull a negative 1 out of everything, and you end up with negative, and then everything flips on the inside. So positive x minus 3. And the bottom, what do you think we're going to do with this? X squared minus 2x minus 3. Right, but what are you doing? You're factoring your magic x, whether you do it in your head or you do it on the side, it's magic x, right? We would say, okay, I got minus 3 and minus 2. What are the two numbers? Minus 3 and plus 1. So x minus 3 and x plus 1. Okay. Luckily, because we did our work correctly, we found out that we can do what? Cancel, right? I can cancel this and this. And that leaves me with a factored form of negative 1 over x plus 1. Right? So far? So good? Okay. So, now, well, we did that in order to find pieces. So what should we find next with our new factored form that we have? Holes? Okay, so where do you find the holes? Holes happen when we, say again? Cancel. So I say, okay, for the holes, what canceled? So there's just the one hole at x minus 3, or when x equals positive 3, right? Because it's about what would make that 0, right? Now, I want to find the y value of my hole, so what do? Say again? Plug it into here, and then I'll get the y value of my hole. So y equals negative 1 over 3 plus 1, which is negative 1 over 4. So where is my hole? Yep, 3 negative 1/4, or negative 0.25, right? So I've got one at 3 negative 0.25, right? Leave it as a fraction if you want. I'm only changing it to a decimal because it helps you estimate a little bit. So at 3 negative 0.25, about right there, I have a hole. Okay? All right, next up. Yeah?
How do you get the negative 0.25?
I plugged in 3 into that. And that gave me the y that goes with it. Okay? All right, next up, vertical asymptotes happen where? Yeah.
So do you always have to flip the sign
Where?
when you're doing your whole?
Yes, because the reason that this is a problem is because it was a problem before we canceled it. We canceled it, sure, but we're kind of hiding the problem. The problem still exists. What problem still exists even though we canceled it out? 3 is the problem because 3 minus 3 is 0. Now, think about it. If it's a problem, it should make the original function a problem. Think about if you plugged in 3 here to the original function. 3 squared is minus 2 times 3. That's 6, so that's 9 minus 6. 3 minus 3 is 0, right? So when we cancel, we hide some problems, but there's still problems, right? It would still be a problem, and that's where holes come in, right? Okay, so vertical asymptote, well, that's the other problem. Where does that exist? Where's that? So the vertical asymptote, if the hole is what we canceled, the vertical asymptote is the problem that it remains, right? There's still a problem over here. What's this one? -1, right? So I have a vertical asymptote at x equals -1. So that would be right here. Okay? And it's really coming together now. I just need my x and my y-intercepts. Now my x-intercepts happen when y is 0. So I would say 0 equals -1 over, -1 over x plus 1, right? Yep. Okay, so how could that ever be equal to 0? -1 over x plus 1. What x could I plug in to make this 0?
Don't you want to take the top?
Exactly, right? There's nothing that I could do on the bottom to make this 0, right? Even if I plugged in a -1, now I'm undefined. It's not going to make it 0. And then the top, can I change anything on the top to make it? No, because there's no x on the top, right? So 0 doesn't equal -1, so there's no x-intercept. Now, we already knew that because we had an asymptote there, but we've just proved it and confirmed it, okay? To find the y-intercept, we make x 0. So we say y equals -1 over 0 plus 1. So what is 0 plus 1? 1. So that's -1 over 1. So that's -1. Okay? So that means we have a 0, -1 intercept at y, for y. So that would be right here. Okay? All right, so we have all our pieces. Now we need to graph. Now with these situations, typically you'll have your cross sections, so you'll know, and we know how these work. It's either like here and here or here and here, right? Well, which one is it going to be? Here and here or here and here? I know, how do you answer that? I just said here 5 times. This one or this one? First or second? First, this here and here. Why? Because we have points here, right? If we have points here, there's got to be a curve here. And if there's a curve here, there's a curve here. So I just go with what I got. I go through these. And then on this side, I got nothing. So I just kind of draw a curve and do my best, right? And I got my function. Yeah?
So for the second one, do you just guess?
You guess. Now, in math analysis, I might ask you to do more. And if you wanted to do more, what could you do at -2? If you really wanted to know where that went through, plug in -2 into your function, and then if whatever y you get will give a point to you on that side. So you could always add points. I'm just not required. These problems are long enough, I think. Okay? All right, so that was your example from the homework.